right, it's 9:40, so let's get started. So just a few announcements. Quiz 2 was posted yesterday on Blackboard, so go ahead and start doing that. Homework 1 is out, obviously, so the first part is due Saturday night at midnight, and the second part is due a week from then. So I highly encourage you to at least attempt to do the questions. And solutions were posted for quiz 1 and what we did last week in recitations. So any questions before we get started then?
It's Sunday night.
Oh, sorry?
The homework one. The part one is due on Sunday or Saturday?
Whatever date it says. It might be Sunday night. Yeah, it's the date posted on the, my mistake if it was Sunday. Any other questions before we start? All right, so on the handout, I have 4 questions on the front and 3 on the back. The 3 on the back are meant for you to get some more practice at home because we're definitely not going to be able to get to them. We're going to be able to definitely do the first 3. I'm not sure if we can do the 4th one today. So what was the main thing we talked about last week in lecture? What was the main thing we talked about?
Constructing a DFA?
Yeah, constructing a DFA, but what did we actually work with DFAs? What did we do with them? Okay. Not quite to NFAs yet, the thing in the middle that we did. Well, think about it a different way. What is a language? It's just a set of strings, right? What do you want to do if you see 2 sets? Just stare at them until something happens, right? I want to do something with the 2 sets, like say form the union of those 2 sets, or do an intersection of the 2 sets. What's another operation you might want to consider then? With sets.
Union.
Well, we did union and intersection. What's another one? Complement, right? So I have some universe, so sigma star. If I want to look at the complement, then maybe we can say something about that. So the 3 operations we talked about in lecture were union, I should put these in this order, intersection, and complement. And why did we actually talk about these? Why do we care about these 3? Because we force you to? No, well, why do we care about these? What's the thing that we're studying? DFAs, right? So what would union have to do anything to do with the DFA? What's that? I can't hear you, sorry. But yeah, closure under union, right? So what does that even mean? If I take 2 DFAs, can I somehow form a DFA for the union of their languages? Yeah, that's what closure under union means. That's what closure under intersection means. That's what closure under complement means. So if I am given a DFA, how do I form a DFA for the complement of whatever language that is? Yeah, I changed the final state. So if it was a final state before, I make it not final in the new machine. If it was not final before, I make it final in the new machine. Right? So that gives us closure and complement. It only works for DFAs. What about union and intersection? So if I'm given 2 DFAs, can I make, say for union, can I make a DFA for the union of their languages? Yeah, that's what we were able to show. So how did that actually go? So let's say I'm given some DFAs, M1, which has some states, alphabet, transition, start, state, final states, and M2, almost the same thing, but with 2s. So if I'm given these two DFAs, how do I form a DFA for their union, let's say? What was the main idea that we thought of in class? Yeah, something to do with pairs of states, right? So what we can think about is maybe I can keep track of what happened in the first machine and what happened in the second machine at the same time. Why would I want to do that at the same time? Instead of just say, run the first machine first and then run the second machine. Why would I not want to do that?
Because you've already seen it.
Yeah, once I consume a character, I'm never ever going to see that character again. So there's no way I can preserve the input for the second DFA. So that's a problem. So the suggestion was, let's just keep track of both states at the same time. So let's make a machine M. And then now I got to figure out all the 5 pieces of this machine. So what are the states going to look like? Well, I'm thinking of something about ordered pairs. I got to keep something of the first machine and something of the second machine. So how do you think I can write the set of all ordered pairs?
Q1 cross Q2.
Right, Q1 cross Q2, right? So this just means I'm going to keep a bunch of ordered pairs. The first coordinate of the ordered pair is a state of the first machine, and the second is a state of the second machine. And so as we're making this, we'll make the transition function work as if we were simulating both machines at the exact same time. But we're really not simulating them, but we're trying to emulate what they would have done. I think the alphabet will stay the same. That's no problem. I'm going to define the transition function in a second because it requires more room. Well, I got to figure out what the start state of this machine is. So I'm going to ask this question several times as we're doing this. What are the states of this machine?
Ordered pairs.
Exactly, they're ordered pairs. So I think that the start state better be an ordered pair because the states are ordered pairs. So I'm going to write an ordered pair. But what is going to go in this ordered pair? Well, the first coordinate, remember, has to be a state of the first machine. So what do you think should be in the first coordinate of this new start state? Q01, the start state of the first machine. Yeah, exactly. And I think the second one's going to be the start state of the second machine, which is Q02 in this case. All right, and then I'm going to define F in a second. Good so far? All right, so let's look at the transition function. So what does the transition function take as input for any DFA? Exactly, it takes a state of the machine and an input of the alphabet, right? Again, what are states of this machine?
Ordered pair.
They're ordered pairs. So the first thing in the transition function better be an ordered pair, right? So I'm just going to invent some names, Q1, Q2. And the character that I'm reading is, say, A, some input character. Well, what is the transition function output to me? Given these two things, what does it tell me? Next state. What are states of this machine? Ordered pairs. So I better write an ordered pair, right? Well, so now I got to figure out what's going to go in this ordered pair. So what do you think is going to go in the first coordinate of the ordered pair? Well, what is the first coordinate keeping track of? The state that if I was just running M1 by itself, that's the state I would have been in. So how do I figure out what this is going to be? Well, I just look up what would the first machine have done. Well, what state am I currently in the first machine in my brain that I'm thinking of? Well, it's in this ordered pair. Which of these states am I currently in the first machine?
Q1.
Q1, yeah. So I'm currently in Q1, and I'm reading an A. How do I figure out where I would have gone in the first machine? Its own transition function, right? It has its own transition function, so let's look up in that. So let's look up in the first transition function with Q1 reading an A. So wherever that takes me, that's what the new first coordinate is going to be. And by the same reasoning, I think the second one's going to be the second transition function with Q2 instead, reading the same character. Okay? So, am I done with this? Have I forgotten anything? Oh yeah, final states. I haven't defined that yet. So, let me ask you a very important question. Was everything that I did, for everything that I've done so far, does that have anything to do with union or intersection? Do I need to get you all a copy or something? No, really. What did that have anything to do with union? No, it had nothing to do with union. So the only thing that differs between union and intersection is the set of final states. Okay? So, well, I just said the final states are a set, so I better write down a set. As always. Again, what are states of this machine? Ordered pairs. So the set of final states better be a set of ordered pairs. So the first, it better be a set of ordered pairs. So now I just got to figure out when I give this name Q1, Q2, what does Q1 have to be? What does Q2 have to be? So let's suppose I'm doing union. So what has to be true of Q1 and Q2 in order for it to say I'm a final state of this new machine? Well, if Q1 was a final state, would this automatically make it a final state?
Yes.
Yes, because I would have accepted in the first machine. If I accepted in the first machine, since I'm doing union, I don't care what the second machine did. As long as I accepted in the first machine. If Q2 was a final state, would you also say that's a final state?
Yes.
Yeah. So I think we can say that this is Q1 in F1 or Q2 in F2. Or both, obviously. Because if both of them are in there, then definitely it's in the union. Oh, let's suppose instead, I told you I didn't want to do union, but I really wanted to do intersection instead. Would I have to do this whole thing again? No, well, wait, what would I change? Oh, I only have to change one word to change this from union to intersection. Okay? Is that clear? All right. So we're going to be using these in the 3 examples here. So the first one is I want all strings in 0, 1 star such that the number of occurrences of the character 0 in this string is not 2. All right? So I don't want to accept the string, for example, 0, 0, but I do want to accept 1, 0, 3 zeros, or any other string that doesn't have exactly 2 zeros in it. All right, so let's try to think, what would be a good strategy to make a DFA for this?
Maybe draw the one that don't want to accept 0, 0.
Oh, I could do that, but what's the first thing of this do you think would be the most important part of this? If you read through this, what is the most important part? Well, the number of zeros, but I think it has to do with this not equal thing, right? It seems like that's the really important part. And if I try to make a DFA like this, that this is not logical reasoning, but let's suppose that I was just starting doing this. Well, then I would have to check whether the number of zeros is equal to 0, 1, 3, 4, 5, 6. I think there are infinitely many possibilities there. It turns out that you don't have to do that, but it seems like that's way harder than than doing some other strategy. So how do you think I can modify this to make this really easy for me? Well, do you think checking against one number is better than checking against infinitely many?
Yeah.
Yeah, so how do you think I can modify this to make it easier for me? Yeah, is equal to 2. Oh, what is that in relation to this set, this language? It's the complement. Oh, can I make a DFA for this guy's complement? Yeah, well, what would that tell me? Can I make a DFA for the original language? Yeah, we just said that we can have closure in the complement by flipping the final and non-final states. Okay, so let's try that. So I'm going to call this thing L, and let's make one for L bar, which is all the strings such that the number of zeros is exactly 2. Okay? So I want to accept every string where it has length exactly 2, or where it has exactly 2 zeros in it. So let's think. If I have 3 or more zeros in the string, and I read the third 0, should I ever accept at that point? For the L bar? No, because I'm never going to ever decrease the number of zeros again. So I can think of this as I've seen 0 zeros, 1 0, 2 zeros, or 3 or more zeros. So let's make a state for each of those 4 possibilities. So I'm going to make the state Q0 to represent I've seen 0 zeros, Q1 seen exactly 1, Q2 exactly 2, Q3 3 or more. All right? What should be the start state of this guy? Q0 because I've seen 0 zeros at that point. Good. What should the 0 transitions do?
Stay on the same.
Stay on the same path. So we did this last week. Similar one. What do you think Q3 does on input 0? It stays there. Good. What do you think the 1 transitions do? They do self loops, right? Because they don't change the number of zeros that I've seen. Good. So 1, 1, 1, and this one's also a self loop. Yeah, because I've seen, if I keep reading 1s and I haven't seen 0 yet, I've still seen 0 zeros. Any other questions at this point? Oh, wait. So another thing about complement. What changes between if I have a DFA and a DFA for its complement? What's the only thing that changes? Final states, right? I don't change the states themselves other than being final or not final. So at this point, the only thing I have left is the set of final states. So let's make the final states for the original guy, right? So for the original one, what would be the set of final states here?
Q2.
For the original one. 0, 1, and 3. Good. So 0 is final, 1's final, 3's final. If we just looked at the complement by itself, we would just make Q2 final by itself, because that's the only case we want to accept. But then when we do the complement, we invert the final and non-final states. Any questions on that? So the whole point of these is, these 3 different operations is to make DFAs for simpler things and then combine them to make that third one. All right, so let's move on to the second one, unless there are other questions. Okay, so the second one is, I want all the strings such that the number of occurrences of 0 is an even number, and the number of 1s in W is exactly 1 or exactly 2. Okay? Oh no, and here, unless it said and. Yeah, exactly 1 or 2. So what do you think the most important part of this definition is then? What's the most important part of this whole thing? Oh, and sounds pretty important, right? That seems pretty important. I want this condition to be true and this condition to be true. Oh, does that correspond to one of the operations we've done?
Intersection.
Oh, intersection. So, what does that mean? If I can make a DFA for the first part and make a DFA for the second part, can I make a DFA for the whole thing?
Yes.
Yeah, I just showed you how we were able to do that. So let's make a DFA for each of the two parts. So I'm going to call L1 to be the first one. So it's all the strings such that the number of zeros is even. All right? Can we make a DFA for that?
Yeah.
Yeah, how would we do that? Oh, yeah, we actually were able to see this in class and recitations last week. We can have a state corresponding to, we've seen an even number of zeros, and another state which corresponds to seeing an odd number of zeros. So I'm going to make two states, Q even, Q odd. What's the start state? Q even, yep, because we've seen 0 zeros. Where does Q even go on 0? The Q odd, because if I've seen an even number of zeros and I read one more, I've now seen an odd number. What does Q even do on 1? Stays there, doesn't change the number of zeros like before. What do you think odd's going to do on both inputs then? It's going to come back on what? 0, good. And what's it going to do on 1? It's going to loop again, yeah. And what is the set of final states? Q even, yeah, because that's the only condition I want to accept for. Nice. So now I want to make one for exactly 1 or 2. So let's make DFA L. I'll do that. So L2 is all the strings such that number of ones is exactly 1 or 2. Wait, this sounds a little familiar. Have we seen something similar to this? Like checking whether it's exactly 1 or 2. Have we seen something similar? Yeah, we actually saw it up here when we made the one for exactly 2, or not equal to 2. But it sounds like it's very similar to this. When we did the L bar one, what would have been the final states? When it was exactly 2. Oh, it would have been just Q2 by itself. Now, if I did the one for 1 or 2, what would the final states be in that case? It'd be Q1 and Q2 being the final states. Oh, wait. This one says the number of zeros is 2, but this one says the number of ones. Oh, yeah, I can just swap 0 and 1 in that case, the roles of 0 and 1. So let's do almost the exact same thing we did before. So let's make Q0 again, Q1 again, Q2, Q3. Q0 is again the start state. But now the 1 transitions are going to go across the states, and the 0 transitions are going to be self loops. Because I want to count the number of ones in this case. And the ones are going to go across. And then, what are the final states again? Q1 and Q2, because I want to recognize seeing exactly 1, 1 or exactly 2 ones. So this guy's final, and this guy's final. Okay? Any questions about any of this? Okay. So am I done with this whole problem? Oh, what have I forgotten?
The end.
Oh, doing the intersection process. What kind of construction is it called? Starts with a P. Product construction. Why is it called product construction again? Because I'm doing the product of the two, the Cartesian product of the two set of states. So let's figure out what this DFA is going to even look like. How many states am I going to have?
8.
I'm going to have 8. Why? Because I got to make an ordered pair with even as the first coordinate, and each one of these as the second, odd as the first coordinate, and each of these as the second coordinate. So I'm going to have 8 states. And the way that I usually write this is with 2 subscripts. So, for example, Q even 0 corresponds to being in Q even in the first machine, Q 0 in the second machine. All right? And so now I'm going to make a Q even 1, Q even 2, Q even 3, and then the odd ones. Q even 1, Q even 2, Q even 3. Q odd 0, Q odd 1, Q odd 2, Q odd 3. Okay? What's the start state of this guy? Yeah, it's Q even 0. And how do we know that? Because if we look at the formal definition of how we did it, it was the original 2 start states of the original 2 machines. And it was Q even here, Q 0 there. So it's Q even 0 there. Just remember, the names of the states don't mean a single thing. I can call this Fred 1, Fred 2, it doesn't matter. But for us, it's really easy to check, okay, this corresponds to being an even in the first machine, 0 in the second, so it's easier for us. Okay, so now all we have to do is the transition function and final states. So I'm going to leave the final states to the end, and let's do the transition function. So what do you think Q even 0 does on input 0? Yeah, let's think about it. So this corresponds to being in Q even in the first, Q 0 in the second. So I got to figure out from both of these states, where would I have gone on 0? So Q even, where does it go on 0? It goes to Q odd. So in my brain, I'm going to write down odd. Q 0, where does it go on 0? It comes back to itself. So I write down 0 in my brain. So Q odd 0. Oh, I have that state, so let's go there on 0. Where does Q even 0 go on 1? Well, I got to figure it out. Where does Q even go on 1? It goes back to Q even through the self loop. So I write even down. Where does Q 0 go on 1? It goes to Q1. So even 1 in my head. Let's do odd 0 now. So I'm in odd 0. Where do I go on 0? So where does odd go on 0? It goes back to even, so I write down even. Where does 0 go on 0? Back to Q0. So I write even 0. Where does odd 0 go on 1? Odd 0. Where does odd go on 1? It goes back to itself, so I write down odd. Where does 0 go on 1? Go to Q1. So I write down odd 1. Do you see a pattern showing up? It's not always the case that you'll see a pattern when you do this, but do you see a pattern here? Yeah, what does the pattern say with the 0 transitions? Yeah, well, let's think about it. It seems like they're going to go across the odd and even row. Well, in the original machine, I know that they'll, no matter what state you're in, you're going to always go to the other state. So no matter what row you're in, when you read a 0, you must go to the other row. Okay? But do you stay in the same column? Well, that corresponds to this machine. Well, each of the states has a self loop on 0. So that must mean, since this is the 1 column, 2 column, 3 column, I stay in the same column. So what do you think Q even 1 is going to do on 0? It's definitely going to go to odd, but it stays in the same column because I know one self loops on 0. So it comes down here. Q odd 1 on 0. Q even 1. What do you think the 2 ones are going to do on 0? The same thing. They're going to go between each other on 0. Good. What do you think the 3 ones are going to do? Same thing. 0. Am I done? Oh, what have I forgotten? Oh, the 1 transitions. Do you see a pattern with the 1 transitions? Let's do one more. Q even 1 on 1. Where is that going to go, do you think? Q even 2. And why do you think that? Oh, well, do you stay in the same row no matter what state I'm in? Well, let's think. The rows are even and odd. No matter what state I'm in the first machine, I'm going to stay in the same state when reading 1. So no matter what state I'm in, I'm going to stay in the same row. But do you always progress to the next one? Well, in the second machine, we always go to the next one when we see a 1. So that's why we were able to deduce that Q even 1 goes to Q even 2 on input 1. What do you think Q odd 1 is going to do on input 1 then? Q odd 2, yeah? What do you think the 2 states are going to do on input 1? They're going to go to state 3, the 3 ones in the same row. Good. Oh, wait, there's no more to go. Where are the 3 ones going to go on input 1? Oh, they're going to stay there. Why? Because in Q3, we're going to self-loop on input 1, and no matter what state we are here, we're going to also self-loop on 1. So no matter which of these 2 we're in, we're going to self-loop on input 1. So 1 here, 1 here. Again, it's not always the case that you'll see a pattern like this, but sometimes it's really nice to actually see a pattern happen there. Am I done now? Oh, final states, yeah. But wait, so did any of that have anything to do with union or intersection? Nope. So this is the only thing that has to do with intersection. So how do I find out what the final states are going to be of this machine? Well, that corresponds to being in a final state of the first machine and a final state of the second machine. Well, how do I find what those are?
You check the first machine versus the second machine.
Yeah, so I have to be in Q even of the first machine. And what states do I have to be in the second machine? 1 or 2, yeah. So it's either Q even 1 is the final state, or Q even 2 is the final state. And that's it. Any questions on any of that? Okay. So let's do number 3, or at least try to. So the question is, the number of zeros is even, or the number of ones is not a multiple of 3. So what do you think is the most important word in that definition? Or, oh wait, so what operation does that correspond to? Union, okay. So if I can make a DFA for both pieces as before, now we can make a DFA for the union of those 2. All right, so the first one is number of zeros is even. Oh, that sounds very familiar. Did we do that one already? Yeah, we did it right here. So the really nice thing about this is that I can reuse DFAs that I've already made before. So what I'm going to do before I erase this is just copy this DFA over. So this one is the number of zeros is even 1, and then I'm just going to copy it over. It's even Start state 0, 0, 1, 1. All right. Does anyone need the product DFA we did last time? All right. So I'm going to write the second DFA in a more unusual way that you've seen, but it's going to actually be very helpful for us. So the second DFA is the number of ones is not a multiple of 3. So how do you think we can tackle that one? Well, we can do complement, but let's try to do it more succinctly. But what's the more general strategy when you see multiple of 3? Yeah, the remainder, right? So how many possible remainders are with 3? 3, 0, 1, and 2. So let's make each one of those a state. So let's make Q0, Q1, Q2 like this. And there's a reason I'm doing it vertically. What's the start state of this? Q0, just like we've seen before. So a couple of people got confused on Monday that this is not the binary representation of the number is a multiple of 3. What I'm checking is the number of ones. So it's a lot simpler than doing binary here. So let's think. What is Q0 going to do on 0? It's going to self-loop. And why is that? Because if I've seen a multiple of 3 number of ones, seeing another 0 is not going to change that fact, right? Oh, what do you think these two states are then going to do on input 0? Same thing, because it doesn't change the number of ones that I've seen. All right. What is Q0 then going to do on input 1? I think it's going to go to Q1 because if we've seen a multiple of 3 number of ones and we see one more, now we have a remainder of 1 if we try to divide by 3. So we should go to Q1. What do you think Q1's going to do? Q2 for the same reason. Oh, what is Q2 going to do? It should go to Q3, right? It should go to Q0. Why is that? Because if we have a multiple of 3 and we add 3, we still have a multiple of 3. So we should come back here. Okay. Are we done with this DFA?
Final states.
Final states. So what are the final states going to be? Q1 and Q2 because we don't want exactly multiple of 3. We want every other state. And it would have been just Q0, so we want the other 2 states. So Q1's final, Q2's final. Okay? So, am I done with this? Whole thing? No, I gotta do the union again. So, let's think. How many states are gonna be in this DFA? 6, because it's 2 times 3. So let's do the same thing again. So, the reason I wrote this DFA horizontally and this one vertically is that we can see when we put Q even and Q0 together, we can see, okay, this corresponds to being even, this column corresponds to being odd, this row is 0, this row is 1, this row is 2. So it's a lot easier to figure out, okay, where am I going to actually go? So this is Q odd 0, Q even 1, Q odd 1, Q even 2, Q odd. How do I find what the start state is? Well, it's the start state of both machines, which is even and 0. So that's the new start state. I'm going to do final states at the end. So let's figure out what the transitions we're going to do. So what do you think Q even 0 is going to do on 0? Well, I look here and I say, where does it even go on 0? Oh, it goes over here. Where's 0 going to go on 0? gonna stay there. So I'm just gonna go across the row here. Where's even 0 gonna go on 1? Well, look, where does even go on 1? Stays there. Q0 on 1 goes down a row. So I'm in this row, in this column. Oh, that's just even 1. You see why I wrote it like this? It's a lot easier. Where does odd 0 go on 0? Well, it definitely goes over to even, but it also stays in the same row because Q0 looped on itself. So it comes back here. Oh, do you see a pattern here? Yeah, again, we have another pattern. Zeros in this machine go across the columns, and whatever row we're in, we're going to stay in the same row. So what do you think the 1 states are going to do on input 0? They're going to go across because these ones go across, but they stay in the same row. So these ones are going to go across, and we can reason that the 2 states are also going across. Oh, what do you think the 1 transitions are going to do?
We'll go down.
They're going to go down, right? Because they stay in the same column, but they progress 1 row at a time. So we can reason that even 1 is going to go down to even 2, and the odd ones are going to come down here. And my time with the transitions.
We still got to loop to 0.
Oh yeah, I got the 2 states don't have a 1. Well, let's think. It's going to stay in the same column, but Q2 on 1 went back to Q0. So where do you think Q even 2 is going to go on input 1? It's definitely going to be 0, but it's also going to be even. So it's going to go back to even 0 on 1. And what do you think odd 2 is going to do on 1? Go back to odd 0. All right. What are the final states going to be? Remember, we're doing union here. So what is going to be union? Okay, so it's either we're in even or we are in 1 or 2. Well, so that must mean every single even state is going to be a final state. So all 3 of these are going to be final. And every 1 state is going to be final, and every 2 states is going to be final. Well, I already marked this one, so I just have this one to go. And this one I have to mark. So the only non-final state is odd 0. Okay, any questions about that? So I definitely won't have time to do number 4, but let's actually try to motivate doing number 4. So what is the most important part of the description of question 4 then? But not both, right? So let's try to modify this one, but to say but not both. Do I need to do this whole thing again? Yeah, I'll have to change this final states again. So how do I find out what states to change here? Well, what states should I take out to be non-final?
Ones that are even and
when we have both conditions being true, when we're in the what of the 2 languages? Intersection, right? So we can tell that the but not both one is just union and take out the intersection ones. So let's think, what are the intersection states here? Well, we're going to be both even and 1 or and 2, right? So I got to remove even 1 and even 2 from being final. So this guy's not final anymore. This one's going to be in the state, and this one's not final. What does that take, like 10 seconds? And the other one took like 10 minutes? So it's a lot easier once you have DFAs to actually combine them to make larger DFAs. Right, I have 6 minutes, so do you guys have any questions about any of the material stuff? questions? All right, I'll see you next week. Yeah, never mind.
Can you have sigma as an empty set because in chapter number 0 it's written that sigma has to be a non-empty finite set, but in the quiz the answer was it could be empty finite set.
Was in chapter 0 sigma defined for
Yeah.
DFA?
Not for DFA, but it was for
So
string.
that's the difference. Yeah. So that's actually a very good question. So can we have sigma to be the empty set? The answer is obviously yes, because that's what the quiz answer was. But how do we reason about that? And if we can, what do the DFAs look like? Well, there's nothing in the definition that says sigma has to be non-empty. There's nothing in the definition that says that. The only place that that sigma actually shows up is in the transition function, which is q cross sigma, it goes to q. That's the only place where sigma shows up. And so I could have an empty set here because I don't have a restriction on that. But would I have any transitions?
No.
No. So I will have 0 transitions. So how many states can I have? Well, I have to have at least one. I may have more than that. But let's just say that we only have one state. So I'm going to call it Q0. Well, then, say, since I can't have any transitions, what are the possible DFAs that could happen here? Well, I could have this one, or what's the other possibility? I didn't mark this as accepted, right? So the other DFA is the exact same thing, but as final state. So, yeah, did you have a question? So, what is the language of the first one? It accepts nothing, right? So what language is it? The set has no members. What is the set that has no members? Empty set. So this one's empty set. What is the only thing that this could possibly accept? Empty string, right? So does the set containing the empty string? This will actually show something very important. Does this DFA accept every string over the alphabet? Yeah, because I can't have any transitions, right? There are no transitions to apply. So, what is the alphabet again? It's the empty set, right? I've defined this to be the empty set. So it accepts sigma star because it accepts every single string. But that's just the empty string. So this actually shows that the set containing the empty string is the empty set star. All right? So here's an important question. No matter what alphabet I have, is sigma star an infinite set? Is it an infinite set all the time? No, because I just showed you that if I set sigma to be the empty set, sigma star is just the set containing the empty string. It only has one string in it. So that's the only case where it's not infinite. Okay? Any other questions? All right, I'll see you next week.